The beam schedule on plans needs to be interpreted well to carefully plan out the number of bars and intersections required for each beam. Practice the process here in quantity surveying. For a single span beam of 6.2 meters clear span, we are to estimate the Steelworks. The beam schedule is also provided, which contains the size of the beam and the rebars for each location, including the stirrups spacing. First is to interpret the beam schedule. Check the top bars, which has 5D20 on the left support, 2 at midspan, and 4 at the right side. With these values, we can then conclude that there are 2 D20 bars continuously placed from the left end to the right end of the beam. Next is to place the cut bars. On the left top support, there is a total of 5 bars, which means there are 3 cut bars. On the right support, the total is 4 bars, which shows that there are 2 cut bars. At the bottom, the bars are written as 3, 6, and 3 in the schedule. This shows that there are 3 diameter 20 mm bars continuously placed in the beam. And then, there are another 3 rebars on the midspan. After learning about the location of the cut bars, identify the number of bars in each span so it would be easier to determine the number of intersections for the tie wire later. From the left column, the first span is measured as an eighth of the CS, and this is computed as 775 mm. This span is free from the midspan bar. The second considers the length of the top support bars, which is taken as a third of the clear span in reference to the ACI standard. With this identified, we can take the difference of these two to have the second span as 1291.67 mm. The third span is bounded by the 2 cut bars on top, which shows that this is measured as a third of the clear span, and this is computed as 2066.67 millimeters. Then from the center line, there is symmetry of span lengths. Thus, the next span is 1291.67 mm, and the right support also has 775 millimeter length. With the lengths already provided, count the top and bottom bars on each. From the first span of 775 mm, check that there are 2 continuous bars and 3 cut bars on top. That makes 5 bars, while there is only the continuous bar at the bottom, which is 3D20. For the second span of 1291 mm, the top bars are counted as 2 continuous and also 3 cut bars, which account to 5. And the bottom bars have 3 continuous and also 3 cut bars, and that is 6 total. For the middle span, there are 2 D20 on top and the continuous bars with 3 cut bars at the bottom, totaling to 6 D20. The span after has 2 continuous top bars with 2 cut bars, accounting for 4, while at the bottom there are 3 continuous and 3 cut bars, resulting to 6 D20. For the last span, there are 2 continuous and 2 cut bars on top, giving 4 bars, when there are only 3 continuous bars at the bottom. Now for the lengths. Categorize each type of bar. First, there are the continuous bars, which can be seen as 2 on top and 3 at the bottom. The length of the continuous bar is computed as the clear span plus 2 development lengths on both ends. With the development length computed as 50D, we get 6,200 plus twice of 50 times 20, and that is 8.2 meters. Then we can conclude that there are 5 pieces of diameter 20 mm rebars by 8.2 meters. Next is the top left support. From the plan, it was identified that there are 3 D20 bars with the length measured as a third of the clear span plus 1 development length. That is a third of 6,200 mm plus 50D, which results to 3,066.67 millimeters. Thus, the top left support bars can be written as 3 pieces of D20 RSB by 3.07 meters. For the right support, there are 2 D20 with lengths measured similarly as the top left support, and that is a third of 6,200 plus the development length, giving 3,066.67 mm. So there are 2 D20 bars by 3.07 meters for the top right support. The last type of bar is the bottom midspan, which from the interpretations taken as 3 D20 mm. Its length is 3/4 of the clear span, and that is 3/4 of 6.2 meters, which gives 4.65 meters. So the bottom midspan bars can be taken as 3 D20 mm RSB by 4.65 meters. Furthermore, complete the row for main reinforcement as the summation of top and bottom bars in each span. The first is 5 plus 3, giving 8 bars. The second span contains 5 plus 6, or 11 rebars. The middle third of the beam has 2 top and 6 bottom, resulting to 8 rebars. Then, the next span has 4 top and 6 bottom, which account to 10 rebars. The last span has 4 top and 3 bottom, or that is 7 rebars. Moving on to estimating the stirrups, start with the length. The size of the beam is 400 by 500. Take out the clear cover in solving for the perimeter of the stirrups. So for the width, which is tagged as A, this is then computed as the width less twice of the clear concrete cover on both sides. That is 400 minus twice of 40, which is 320 mm. The height of the stirrup, tagged as B, is computed as the height less 2 times the clear concrete cover, or 500 minus 2 times 40, and that is 420 mm. The length of the stirrup is then measured as twice of A and twice of B plus the 2 hooks. That is twice of 320 and 420 plus twice of 9D. This is 640 plus 840 plus twice of 9 times 12 mm, which equals to 1,696 millimeters. For the quantity, the way to estimate this is by laying out the stirrups on the beam, using the designed spacing for each. The beam schedule included the number of stirrups with their designated spacing. To start with the laying out, take the center line of the beam. This cuts the beam length into half. Thus, the center line for this example is at 3.1 meters. From the column face, The first two stirrups are spaced at 50 mm, which consume 100 mm. The next is three stirrups spaced at 75 mm, which use another 225 mm. This is followed by another three stirrups spaced at 100 mm, making 300 mm. The next are spaced at 125 mm, which use another 625 mm from the length. Then, reading from the beam schedule, it was written that the rest of the length uses 150 mm spacing for stirrups. But what is the remaining length? Half the beam is 3.1 meters, then take out the lengths used up by the previous stirrups. This gives 1.85 meters remaining, and by this length, the stirrups spacing to be used is 150. So 1,850 divided by 150 gives 12 more stirrups. Now check for the remaining space. 12 times 150 is 1.8 meters, which leaves 50 mm to center line. If this is mirrored, making the length 100 mm is still less than the maximum spacing of 150, so no need to add any other stirrup. Now list the distribution of stirrups under the proper span. The first span has 9 stirrups. The second span also contains 9. The middle span carries double of the remaining bars as they should be mirrored from the center line. There are remaining 7 bars to center line. Have this mirrored to get 14. Then the last two spans carry 9 bars each. To complete the estimation, remember that the beam column intersection needs 3 stirrups. So there are 3 on the left beam column connection and also on the right connection. Now add all the number of stirrups to find out that there are 56 in all. Also complete the table to find the number of intersections, which is the product of the main bars and the stirrups. From the left column connection, 8 times 3 gives 24. Next is 8 times 9 giving 72. Then the next span has 11 by 9, which is 99. And the middle span takes 8 times 14, which is 112. The succeeding span is 10 times 9, which is 90, with 7 times 9, and that is 63. And the right beam column connection has 7 times 3, or 21 intersections. Take the total of intersections, and that is 481. To estimate the tie wire, take the 481 intersections multiplied by the required length of the tie divided by the conversion factor of 53 meters per kilogram. That is 481 intersections by 0.3 meters per intersection, and there are 53 meters in a kilogram. This results to 2.47 kg. So in summary, there are 5 D20 by 8.2 meters continuous bars, 3 D20 by 3.07 meters top left support bars. The top right support also has 2 D20 bars by the same length. Then, the bottom midspan contains 3 bars by 4.65 meters. With the same lengths of bars at the supports, we can summarize them as 5 D20 RSB by 3.07 meters. Next is 56 D12 bars by 1.696 meters stirrups, tied by 2.72 kilograms of gauge 16 GI tie wire.